Roughly 70,000 years ago, while early modern humans were painting on cave walls and crossing land bridges into new continents, something slipped through the outer edge of our solar system. Close enough, astronomers now calculate that it would have been visible in the night sky of our ancestors. Nobody saw it. There was no telescope, no written record, no warning. It was a star. A dim, faint red dwarf, tumbling through the darkness with a small companion in tow, passing within roughly 0.8 light-years of our sun, close enough to nudge the outer edge of our solar system's most distant, faintest structure. Close enough that, if it had been slightly larger, slightly brighter, slightly closer, it might have visibly disturbed the delicate gravitational balance holding our solar system's outer reaches together. We only found out this happened at all in 2015. Not by watching it happen, by reconstructing it afterward, working backward through decades of stellar motion data. Like detectives arriving at a crime scene 70,000 years too late, piecing together exactly what happened using nothing but trajectory and math. Astronomers named it Scholz's star. And the more they studied it, the more unsettling one particular implication became. If a star can pass this close to our solar system without us noticing until 70,000 years after the fact, what else has passed by that we still don't know about? And more importantly, what's coming next? Let's start with how something this significant went completely undetected for so long, because the answer reveals something genuinely humbling about the limits of even modern astronomy. Scholz's star is what astronomers call a red dwarf, a small, cool, dim type of star, far less massive and far less luminous than our own sun. Red dwarfs are actually the most common type of star in the entire galaxy, making up an estimated 70% or more of all stars in the Milky Way. But because they're so faint, they're also incredibly difficult to spot unless they happen to be relatively close to us, or unless we're specifically looking in exactly the right place at exactly the right time. The star wasn't discovered until 2013, catalogued during a routine astronomical survey, sitting at its current distance of roughly 20 light-years from Earth, reasonably close, in cosmic terms, but far enough away and dim enough that it had simply gone unnoticed for a very long time. At first glance, it looked like nothing particularly special, just another faint, unremarkable red dwarf, one among billions scattered across the galaxy. Then, in 2015, a team of astronomers, led by Eric Mamajek, decided to take a closer look at its motion, specifically its radial velocity, meaning how fast it's moving directly toward or away from us, and its proper motion across the sky. And something immediately stood out as strange. Most nearby stars show a fairly noticeable amount of what astronomers call proper motion, a gradual drift across the sky over time, as we view their movement from our own vantage point. Scholz's star showed almost none. Its motion across the sky was barely detectable at all. At first, that might not sound alarming, but to an astronomer, it's genuinely strange, and here's why. A star's proper motion depends heavily on the angle at which it's moving relative to us. If a star is moving mostly sideways across our line of sight, its motion becomes very apparent over time. But if a star is moving almost directly toward us or almost directly away from us, its sideways motion across the sky becomes minimal, even if it's moving at a substantial actual speed through space. Scholz's star's nearly non-existent sideways drift, combined with its measured radial velocity, meant one thing. It wasn't moving sideways past us. It was moving almost directly along our line of sight, either coming toward us or having already passed by, moving directly away. When Mamajek's team ran the numbers, reconstructing the star's trajectory backward through time using its current position, speed, and direction, the result was startling. Roughly 70,000 years ago, Scholz's star wasn't 20 light-years away. It was passing directly through the outer faint edge of our solar system's most distant region, a vast, sparse shell of icy debris called the Oort cloud. Let's talk about exactly what that means and why it matters so much, because most people have never even heard of the region this star actually passed through. The Oort cloud is a theoretical, though strongly evidence-supported, spherical shell of icy debris believed to surround our entire solar system, starting somewhere beyond the orbit of Pluto and extending outward for an almost unimaginable distance, potentially as far as 1 to 2 light-years from the Sun, nearly a quarter of the way to our nearest stellar neighbor. It's thought to be the source of long-period comets, icy leftover material from the formation of our solar system. drifting so far out in the cold and the dark that individual objects within it can take millions of years to complete a single orbit around the sun. We've never directly observed the Oort cloud, not once. It's simply too distant, too dark, and its individual objects too small and faint for any current telescope to directly image. Its existence is inferred almost entirely from the behavior of long-period comets, whose highly elongated extreme orbits strongly suggest they originate from a vast, distant reservoir exactly like this. According to Mamajek's calculations, Schultz's star, along with a small companion star orbiting alongside it, a faint object called a brown dwarf, sometimes described as a failed star, too small to sustain the nuclear fusion that powers true stars, passed within roughly 0.8 light-years of our sun during this ancient encounter. That's remarkably close in cosmic terms. For comparison, our very nearest confirmed stellar neighbor today, Proxima Centauri, sits at a distance of 4.24 light-years. Schultz's star, 70,000 years ago, came more than 5 times closer to us than our current nearest neighbor is right now. Some researchers involved in the original study estimated that the encounter had a reasonably strong probability of passing directly through the outer boundary of our solar system's Oort cloud, based on the uncertainties involved in reconstructing its ancient trajectory. If that's accurate, it would make this the closest documented stellar flyby in the recorded history of our solar system. Now here's the detail that should genuinely give you pause. This wasn't calculated using a telescope pointed at the past. There's no way to do that. This was calculated entirely through mathematics reconstructing a star's motion backward through 70,000 years of time, using nothing but its current position, current speed, and our understanding of gravitational mechanics. We didn't watch this happen. We deduced that it happened, entirely after the fact, using evidence the universe simply happened to leave behind in the star's present-day trajectory. Which raises an obvious, uncomfortable question. If we only found out about this encounter by accident, decades after developing the technology and technique to reconstruct it, how many other close stellar encounters throughout our solar system's entire history have we simply never noticed at all? Let's talk about why a close stellar flyby like this actually matters. Because it's not just an interesting historical footnote, it touches directly on the long-term safety and stability of our entire solar system. The outer Oort cloud is an incredibly sparse region. The icy bodies within it are spread across such an enormous volume of space that they're typically millions of kilometers apart from each other, drifting slowly under the influence of extremely weak, distant gravitational forces, primarily the sun's gravity, but also, at these extreme distances, subtle gravitational tugs from the wider galaxy itself, and, occasionally, from passing stars. When a star passes anywhere near this fragile, loosely bound structure, its gravity can potentially disturb the orbits of these icy bodies, nudging some of them out of their long, stable paths. Some might get flung entirely out of the solar system altogether, lost forever into interstellar space. Others might get gravitationally redirected inward toward the inner solar system, potentially setting a long-period comet on a new trajectory that, over the following tens of thousands of years, could eventually bring it into the vicinity of Earth. To be clear about what's established fact versus what remains genuinely uncertain here, astronomers are confident that stellar flybys like this can, in principle, gravitationally perturb Oort cloud objects. What remains harder to determine and still actively debated is exactly how significant Schultz's star's specific encounter actually was in practice, whether it was close enough, and its combined mass, with its brown dwarf companion, substantial enough, to meaningfully disturb a significant number of Oort cloud objects, or whether the encounter, despite its remarkably close distance, was simply too brief, and the star too small in mass to produce more than a negligible gravitational ripple. Some researchers who've studied the encounter in detail have suggested that any disturbance was likely modest, given the relatively low combined mass of Schultz's star and its companion. But modest, in a system home to potentially trillions of icy objects, still leaves room for real consequences we may not have identified yet. Comets currently en route toward the inner solar system on multi-thousand-year journeys that were nudged into their current trajectories by an encounter our ancestors never knew was happening, tens of thousands of years before any of us were born. In other words, somewhere out there, right now, there may already be a long-period comet quietly making its way toward the inner solar system, its current path a direct, delayed consequence of a star that briefly grazed the edge of our solar neighborhood while early humans were migrating across ancient landscapes, utterly unaware that anything unusual was happening in the sky above them. That's the part of this story that tends to sit uncomfortably with people once they really think it through. This isn't a hypothetical future threat. It's a real, confirmed event from our solar system's actual past, and we still don't have complete certainty about everything it might have already set into motion. Let's widen the lens even further, because Scholz's star isn't actually unique in the sense of being the only close stellar encounter in our solar system's history. It's simply the one we happen to discover and successfully reconstruct. Astronomers using data from the European Space Agency's Gaia spacecraft, the same extraordinarily precise billion-star mapping mission we've discussed before, have identified numerous other stars whose reconstructed past or projected future trajectories bring them into relatively close proximity to our solar system, on timescales ranging from tens of thousands to millions of years in either direction. Most of these encounters, based on current calculations, involve much greater distances than Scholz's star's remarkably close pass, and are considered unlikely to pose any meaningful risk to our solar system's stability. But here's the genuinely important and slightly unnerving caveat buried in all of this research. Our ability to detect these encounters depends entirely on how precisely we can measure a star's current position, distance, and velocity. Gaia has dramatically improved that precision for millions of nearby stars, allowing astronomers to reconstruct stellar trajectories with far greater confidence than was possible before its launch in 2013. But there are almost certainly stars out there, particularly faint ones like red dwarfs and brown dwarfs, similar in nature to Scholz's star itself, that either haven't been cataloged yet at all, or haven't had their trajectories measured with sufficient precision to confidently rule out a past or future close encounter. Scholz's star itself is the perfect illustration of exactly this problem. It sat in astronomical catalogs for years, its extraordinary, unusually close ancient encounter with our solar system completely unnoticed, simply because nobody had yet run the specific trajectory calculation needed to reveal it. It wasn't hiding. It wasn't invisible. The data needed to find it was sitting there the entire time. It just took the right astronomer, asking the right question, at the right moment, to actually notice, which means, statistically, there are likely other stars out there right now, sitting quietly in astronomical databases, whose own remarkable past or future encounters with our solar system simply haven't been discovered yet, not because the evidence isn't there, but because nobody has looked closely enough at exactly the right angle to see it. Let's sit with the emotional weight of this story for a moment, because there's something genuinely profound buried underneath all the orbital mechanics and trajectory calculations. 70,000 years ago, somewhere on Earth, small groups of early modern humans were living through what was, for them, an ordinary night. They had no concept of stars as distant suns, no understanding of gravity, of orbits, of solar systems. If Scholz's star had been bright enough to see with the naked eye during its closest approach, and some calculations suggest it may have briefly been faintly visible, given its proximity, despite its intrinsically dim nature, it would have appeared to them as nothing more than an unusually faint temporary addition to a sky already full of far brighter, more familiar points of light. A curiosity, at most, certainly not a warning. Certainly not evidence that something was quietly brushing up against the outer boundary of the very solar system cradling their entire world. They had no way of knowing. And for tens of thousands of years afterward, neither did we, not until a specific combination of cataloged stellar data, precise motion measurements, and one team of astronomers deciding to run the math backward, finally revealed what had actually happened, at last, in 2015. That's an extraordinary thing to consider. An event significant enough to potentially nudge material at the very edge of our solar system, happening in what is, cosmically speaking, our own recent backyard and our own recent past, went completely undetected for the entire span of recorded human civilization. We built the pyramids, invented writing, crossed oceans, and split the atom, all without knowing that a star had once passed close enough to reach into the furthest, faintest reaches of our own solar system. So the question that naturally follows, and the one that makes this story feel less like ancient history and more like an active, ongoing concern, is simple. Is anything like this happening again? Is anything like this coming? Here, the science becomes genuinely reassuring. at least for the foreseeable, calculable future. Using Gaia's precise stellar motion data, astronomers have projected the future trajectories of thousands of nearby stars, searching specifically for any predicted close encounters over the coming hundreds of thousands of years. The most current research suggests that any future stellar encounters close enough to significantly disturb our solar system's stability, similar in scale to Scholz's star's ancient past, are expected to be exceedingly rare on any timescale remotely relevant to human civilization, let alone human lifetime. That said, rare is doing real work in that sentence, and it's worth being honest about the limits of what we actually know. Our ability to predict these encounters is only as good as our current catalog of nearby stars. And as Scholz's star itself demonstrated, faint, easily overlooked objects can sit undetected in plain sight for a very long time before someone finally notices what their motion actually reveals. Ongoing survey missions, expanding and refining Gaia's already extraordinary dataset, continue to improve our ability to catch these encounters, both past and future, with ever-increasing confidence. So here's the truth we're left with tonight. 70,000 years ago, a dim, unremarkable star and its small companion drifted close enough to our solar system to potentially nudge the ancient icy material sitting at its farthest, faintest edge, an encounter that unfolded in complete silence, under a sky full of unwitting human observers, and remained completely unknown to us until decades of careful, patient scientific work finally reconstructed it nearly 70 millennia after the fact. It's a genuinely humbling reminder that our solar system isn't the sealed, isolated bubble it sometimes feels like from the inside. It's embedded within a much larger, constantly shifting galactic environment, occasionally brushed by other stars drifting through the same vast neighborhood we call home, on timescales so long, and through spaces so empty and dark that we may not even notice when it happens until long, long after the fact. We didn't see the star that came inside our solar system. Not because it was impossible to see, simply because nobody, at the time, had any reason to be looking. And somewhere out there tonight, quietly drifting through the galaxy alongside billions of other stars we've barely begun to catalog, there may already be another encounter unfolding right now, invisible in the data, waiting patiently for the moment, years or decades from now, when some future astronomer finally decides to run the numbers and discovers exactly what's already been happening silently the entire time.